Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. My name is Siti Nurzailyn and today I'll be presenting my paper titled Hazard Identification and Analysis of Explosion Impact on SOFC, Solid Oxide Fuel Cell, Biogas Plant. These are the following topics that I'll be covering in these presentations, including the introductions, problem, research objectives, methodology, and results. To begin, let me tell you a little bit background on this research. I have started this research because I see the potential of biogas as renewable energy sources. It has high potential, and the proof is that we can see the installation of biogas plant has increased globally. However, safety evaluation of SOFC biogas plant is very limited. This actually makes sense because the application is also limited. In fact, there's only one industrial-size SOFC biogas plant available globally, which is located in Italy. Let's take a look at the history of biogas plant accidents. We can see a rise in the number of biogas plant accidents in recent years, and this number is expected to increase even more in future if safety is not taken seriously. When implementing SOFC into the biogas plant, the problem comes from these two systems itself, the biogas plant and the SOFC system. The biogas plant itself involves a huge amount of flammable gases, and these flammable gases, such as hydrogen and methane, are used as a fuel to be fed into the SOFC system. And if we take a look at the SOFC system, it consists of high-risk components such as reformer, heaters, combustor, and the stack itself. And what makes things worse is that it operates at very high temperatures, which is up to 1000 Celsius. And all of this definitely contributes to the risk of fire and explosions. The real question is, how much risk of fire and explosions are we talking about? What's the impact in case of accidents? Can the risk be reduced? And finally, the most important question is it safe to implement SOFC into the biogas plant? So, this research aims to identify the hazards, to develop the CFD model, this is to simulate the explosion phenomena, to carry out the explosion impact assessment, this is to predict the damage done to the plant and personnel, and finally to propose SOP as risk mitigation measures. So these are the general method that I've used in this research. The first one is the Bayesian network model, which is used to identify hazards on the SOFC system. It is also used to determine the parameters contributing to the risk of fire and explosions, and this would be objective 1. Another method used is the F&EI method, the Fire and Explosion Index method, to identify hazards on the SOFC biogas plant. It is also used to determine the radius of exposure in case of an explosion, and also to estimate the economic losses. Another method used is a more advanced method, which is a CFD model, the computational fluid dynamic model, which also to identify the hazards and to carry out a more detailed analysis of explosions on SOFC biogas plant. And this involves the development of geometry, meshing, leakage rate model, model setup, and so on. And this would be objective 2. Once we have the successful simulation of the CFD models, we are able to carry out the explosion impact assessment, and this would be objective 3. Once we have all the results from the analysis of Bayesian network, F&EI, and CFD, we are able to propose the SOP as risk mitigation measures, and this would be objective 4. So this is the results for the first objective, the hazard identification using Bayesian network analysis. And this is the framework of the Bayesian network model that I have developed for SOFC system. From the model, it was calculated that the risk of fire is 21% and the risk of explosion is 7%. When we investigate further, it was determined that the factors contributing the most to the risk of fire is actually due to overheating, while pressure is the factors contributing the most to the risk of explosions. Now that we know the operating conditions are the parameters or factors contributing the most to the fire and explosion, let's see the relationship. As expected, higher temperatures will result in higher risk of fire, and higher pressure will result in higher risk of explosions. But here's the interesting part. Lowering the temperatures can only reduce the risk of fire by 17%. So at this point, this proves that SOFC operating temperature does not significantly influence the risk of fire, meaning that there are many other parameters contributing to the risk of fire. On the other hand, for explosion scenario, we can see that the risk of explosion suddenly increased from 7% to 18%. So this is a little bit concerning for me, which is why I have decided to investigate further on the explosion scenario, which will be discussed on Objective 3. Another method used to identify hazards is the Fire Explosion Index, or F&EI analysis. And from this analysis, it was identified that biogas storage tank has the highest F&EI index with severe degree of hazards, while SOFC has the lowest F&EI index with moderate degree of hazard. And the economic losses is estimated to be 4.38 billion ringgit for biogas storage tank and 0.86 billion ringgit for SOFC. So F&EI is generally used as initial assessment to predict the potential hazards. So in this case, we're using F&EI as initial assessment before we use a more advanced method, which is the CFD method. For example, in the case of explosion on SOFC, this is the area of exposures, and this will affect the anaerobic digester unit only. But in case of explosions at the biogas storage tank, it will cause a bigger area of exposure, therefore will influence more process units and will result in greater impacts. Second objective is to develop the CFD model, and this is the results for geometry and meshing. So the geometry is developed based on the existing biogas plant in Malaysia. So this is actually based on the actual dimensions. And this is the results of the meshing. So meshing is very important because it determines the reliability of the CFD model and also to reduce the simulation time. So it's important for us to choose the correct size of mesh. So I have conducted mesh independent study to see how these different sizes of mesh influence the results. And as you can see, these three sizes of mesh have more or less the same results, but the simulation time is very, very different. For ultrafine, the simulation time is 143 hours and medium size is only 13 hours. So at this point, it is wise for me to choose the medium size for our mesh. To confirm the selections of the mesh sizes, I have conducted another mesh independent study, and again the results are the same. So now that we have confirmed our mesh sizes, which is the medium size, we are now ready to start our simulation. To simulate the worst case scenario, we have to determine the ignition time. Ignition time is selected when the fuel cloud is formed at its highest concentrations. And from the figures, we can see that at flow time is equals to 10, the fuel cloud is formed at the highest concentrations compared to other flow time. So the ignition time is selected to be 10 seconds. So this means that the explosions will only occur after 10 seconds of fuel leakage. This is the explosion simulation to see temperature distributions, and if you see a sudden increase in temperatures, then that's the indication of explosion occur, which is now. So this is the temperature profiles that I've extracted from the simulations. As you can see here, at any locations, we are able to know exactly what temperatures is at that locations. So this is how I predicted the explosion impact in terms of the thermal effects from the simulation. This is the explosion simulation to see the pressure distribution, and also the same if we see a sudden increase in pressure, that's the indications of when the explosion occur. From the simulations I have successfully obtained the explosion plot, which I have extracted from the simulation. And as you can see here, the explosion process is only within 0.05 seconds, and the peak of the pressure is around 35 kilopascal. Now that we have a successful simulations that we can obtain our explosion plot, we can now investigate the parameters influencing the explosion impact, starting with the SOFC temperature. So the SOFC temperature is varied from 600 Celsius to 1000 Celsius, and this is the explosion profile. So if we look further on the explosion, the peak of a pressure generated, we can see a clear trend. As expected, higher SOFC temperatures results in higher impact. But the difference is only 5 kilopascals. So the difference is not significant. Again, this proves that SOFC temperature does not significantly influence the hazard impact. Another parameter is the wind speed. As you can see here, higher wind speed will result in lower impact. This means that lowest wind speed results in the greatest impact. This is actually in agreement with the theories, as lower wind speed will allow the fuel to accumulate more, and this will result in higher concentrations of fuel cloud being formed. So this will lead to a higher impact in case of explosion. Another parameter is the leakage rate. Although we do know logically that higher leakage rate will result in higher impact, but looking at the highest leakage rate, it results in 1000 kilopascal, while our case study is only 35 kilopascal. So that's how big the influence of leakage rate on the explosion impact. So this means that comparing it with other parameters, leakage rate have the greatest influence on the explosion impact. Now that we have the overpressure and the temperature profiles, we are able to predict the blast impact. In the case of highest SOFC temperatures and the lowest wind speed, to represent the worst case scenario, this will cause a total destruction to SOFC and aerobic digesters and to the sludge cake yard, and it will also cause the biogas storage tank and the sludge holding tank to ruptures and minor damage to the treatment building. But the good news is the admin building, which is the most important area, the most populated area, is not affected at all by the explosions. And in the case of the highest leakage rate, it will cause a total destructions to most of the process units and the buildings. Again, the good news is the admin buildings are not affected by the explosion. For the verifications, the CFD model have verified against the theoretical TNT model, where this model have calculated the overpressure to be 163 kilopascal, while the CFD model have estimated the overpressure to be around 167 kilopascal on average. So the results discrepancy is less than 3%. So this indicates that this model can accurately represent the real explosion phenomena. For validation, since there is limited explosion data on biogas plant, the CFD model has been validated against another validated CFD model from literature, which is from Sajid's study. Sajid has actually simulated an actual explosion from Venezuela and have predicted the overpressure generated to be 7.2 bars, and my CFD model have predicted the overpressure to be 8.8 bar. Although the CFD model developed in this study have overestimated the overpressure by 1.6 bar, comparing it in terms of the explosion impact, the results is actually in agreement with the actual explosion accidents. Therefore, the CFD model developed in this study is still considered reliable. Now that we have completed all the analysis from Bayesian network model, F&EI model, and the CFD model, the SOP can now be proposed. So I have proposed the SOP based on three sections, which is the safety measures, preventions and mitigations, and personnel. For safety measures, it focuses on the safety measures of the SOFC system. I've also classified the hazardous area of the biogas plant according to the zone. As for the prevention and mitigation SOP, it focuses on suppressing or preventing the explosions, including the explosion suppression system, the explosion isolation system, the blast wall, and the relief venting. And finally, the SOP for personnel. So this is also very important because SOFC technology is rather new in Malaysia. So it's important to have training on high operating temperatures such as SOFC, to have training on the procedures, to have a certified individual when operating the SOFC, and of course, to have a specific PPE designs to withstand the thermal radiations. So these are the SOP that I have developed focusing on the explosion scenario. So this is the classification of the hazardous area. So zone 0 is considered as the high risk zone and zone 2 is considered as the low risk zone. So this is actually based on the analysis on the explosion radius that we have identified from the CFD model, from the F&EI and Bayesian network model. I've also recommended to change the location of SOFC, which is initially located here, and recommended it to move to the lower side of the biogas plant. In summary, the hazards of fire and explosion on SOFC biogas plant are identified. The risk of fire is calculated to be 21% and the risk of explosion is calculated to be 7%. Comparing this with the actual event, this risk of fire and explosions are very unlikely to occur. The highest risk unit is also identified to be the storage tank, while the lowest risk unit is the SOFC. Secondly, the CFD model simulation is successfully developed. The model has been verified and validated. Thirdly, the integration of SOFC into the biogas plant is safe. And finally, SOP proposed can be served as the guideline to enhance the safety of SOFC biogas plant. Thank you very much and have a good day.